Welcome to News Beacon, your trusted source for breaking headlines, global insights, and sharp analysis from around the world. If you're new here, don't forget to hit that subscribe button and turn on notifications so you never miss an update. In the high-stakes world of semiconductors, a seismic rumor is spreading, sending shockwaves through the global tech community and boardrooms alike. China may have built its own extreme ultraviolet lithography machine, a feat once thought nearly impossible outside the West. If true, this breakthrough could upend decades of Western dominance, challenging the monopoly of Dutch giant ASML and threatening US technological supremacy. The balance of power in the chip world could shift overnight, with consequences for every industry that relies on advanced computing. Advanced chips power everything from smartphones to AI and military tech. Control over their production means global influence, economic leverage, and even national security advantages. For years, the US has tried to block China from accessing EUV technology, seeing it as a critical choke point in the race for technological leadership and future innovation. Now, whispers from Beijing suggest China may have found a way around this blockade, raising urgent questions about the effectiveness of American strategy and the future of global tech competition. Has the West's pressure only accelerated China's innovation, pushing its scientists and engineers to achieve the unthinkable? As the world waits for confirmation, we must understand the science and stakes behind EUV lithography, the heart of this global rivalry, and the key to the next era of technology. This is a story where physics, engineering, and geopolitics collide, and the control of light itself is the ultimate prize in a contest that could define the future. Chipmaking is, at its core, a process of printing, using light to etch microscopic circuits onto silicon wafers. This process is the foundation of every modern electronic device, from smartphones to supercomputers, and it all starts with the ability to carve out impossibly tiny patterns with incredible precision. Traditional deep ultraviolet, or DUV, light couldn't keep up as transistors shrank. It was like writing with a paintbrush instead of a pen. As the industry pushed for smaller, faster, and more energy-efficient chips, DUV's limitations became a bottleneck, making further progress extremely difficult. Enter extreme ultraviolet, or EUV, with a wavelength of just 13.5 nanometers, over 10 times shorter than DUV, enabling the creation of the world's most advanced chips. This breakthrough allows engineers to draw much finer lines, packing billions more transistors onto a single chip and unlocking new levels of performance. These chips drive AI, next-gen communications, and supercomputers. They're the engines behind everything from cloud computing to autonomous vehicles, powering the digital revolution that shapes our daily lives. Without EUV, manufacturing at the cutting edge is nearly impossible. The most advanced processors and memory chips simply can't be made with older technologies, making EUV essential for staying ahead in the global tech race. ASML, the Dutch company that mastered EUV, holds a monopoly on this technology. No other company has managed to match their expertise or the complexity of their machines, making ASML a critical player in the semiconductor industry. EUV machines are marvels of engineering. They operate in a vacuum, use atomically precise mirrors from Zeiss, and fire lasers at molten tin to create plasma. This plasma emits the EUV light needed for the process, all happening in a highly controlled environment. Each machine costs over $350 million and contains more than 100,000 components. Building and maintaining them requires a global supply chain and the world's top engineering talent. For China, being denied this technology has been a formidable barrier, fueling a national effort to catch up, no matter the cost. The stakes are enormous, as access to EUV is seen as a gateway to technological independence and leadership. Possessing EUV means holding the keys to the future of computing. It's not just about making better chips, it's about shaping the next era of innovation, security, and global power. The US recognized the strategic power of advanced semiconductors, understanding that whoever controlled the most cutting-edge chips would shape the future of technology, economics, and even national security. As China rapidly advanced, the US made blocking China's access to EUV technology a top priority, seeing it as a way to maintain its technological edge and global influence. Export controls, expanded under both Trump and Biden, barred any company worldwide from selling advanced chip-making tools to China if they contained US technology, no matter where the company was based. This move directly targeted ASML, the Dutch company whose EUV machines are essential for producing the world's most advanced chips, and whose critical laser source comes from Cymer in San Diego, making them subject to US rules. The US pressured the Dutch government to block ASML from shipping EUV machines to China, effectively cutting off China's path to the most advanced chips and halting its progress at a critical juncture. The impact was immediate. Companies like Huawei and SMEE were stuck at older process nodes, unable to compete with industry leaders like TSMC and Samsung, who continued to push the boundaries of chip technology. The controls created a technological ceiling, capping China's ambitions in AI, high-performance computing, and other fields that rely on the most advanced chips. But instead of crippling China, the blockade galvanized it, sparking a sense of urgency and determination across the country's tech sector. Beijing saw this as an existential threat and responded with a massive, state-funded campaign for semiconductor self-sufficiency, pouring resources into research, development, and talent. The chip war didn't end, it just shifted the battlefield, turning global supply chains and technology standards into new fronts in the conflict. China began pouring billions into replicating the entire semiconductor supply chain, from raw materials to lithography machines, determined to break free from foreign dependence and secure its technological future. China responded to the blockade with a strategy reminiscent of a space race, massive investment and national mobilization. New champions emerged: Carrier, Yuliangsheng and ASML, each tackling a piece of the lithography puzzle. Carrier patented a technique called self-aligned quadruple patterning, using DUV machines to approach 5nm performance. Yuliangsheng developed 28nm DUV immersion lithography machines, a major step for China, proving mastery of complex optics and mechanics. Meanwhile, Huawei pivoted to fundamental semiconductor research, exploring experimental alternatives to ASML's EUV technology. Together, these companies form a coordinated front, building DUV tools, developing workarounds, and pursuing next-gen EUV. China's approach attacked the problem from every angle. China's most practical strategy isn't building an EUV machine overnight, but pushing DUV technology to its limits. The key self-aligned quadruple patterning, SAQP, a process that uses DUV machines in multiple steps to achieve fine lines. This workaround allowed SMEE to produce chips approaching 5nm performance, likely powering Huawei's latest smartphones. But the process is slow, complex, and expensive, with yields as low as 33% and costs up to 50% higher than TSMC's EUV-made chips. It's commercially unviable for mass-market products but acceptable for low-volume, high-priority uses. The DUV detour is a strategic stopgap, buying time and experience. Ultimately, to compete globally, China must master EUV. The workaround is a bridge. EUV remains the destination. While the world focused on front-end lithography, China quietly excelled in advanced packaging, the back-end of chip-making. ASML, spun off from state-owned SMEE, rapidly dominated China's market for packaging lithography machines and captured 35% of the global market. In August 2025, ASML shipped its 500th stepper machine. A month later, its next-gen system won a major industry award. This success gives China leverage in the global supply chain and generates revenue and expertise for front-end efforts. ASML proves that China's state-backed investment and commercial spin-offs can deliver world-class results. While EUV remains the ultimate goal, ASML shows China's path to self-sufficiency is multi-pronged. Victories in packaging are real and strategically significant. China's progress isn't all or nothing, it's a series of tangible wins. Despite China's progress, ASML's dominance is built on more than just superior machines. It's a global ecosystem refined over decades. An ASML EUV machine is a symphony of over 100,000 parts, sourced from more than 100 top-tier suppliers. Key partners like Zeiss, Mears and Cymer laser source are monopolies in their fields, with exclusive long-term relationships. Replicating ASML means recreating this entire network, not just the hardware. The real gap is in operational knowledge, institutional expertise, and collaborative trust built over years. ASML's CEO estimates China is 10-15 years behind, but the true barrier is the mountain of proprietary data and know-how. This global interconnected ecosystem is ASML's true fortress. For now, its position at the top of chip-making remains unassailable. China faces a challenge of a completely different magnitude. Recognizing the near impossibility of copying ASML's supply chain, Huawei is exploring radical alternatives for generating EUV light. Instead of ASML's laser-produced plasma, Huawei is testing laser-induced discharge plasma, a high-risk, high-reward shortcut. This method could bypass some of ASML's most protected technologies, but comes with immense engineering challenges. Early reports suggest Huawei's approach lags in power and stability, far behind ASML's decades of refinement. To close the gap, Huawei is also aggressively recruiting top talent from ASML's partners, offering huge salaries. If China can't buy or copy the technology, it aims to hire the brains behind it. This two-pronged strategy, novel physics and talent acquisition, shows China's determination to break through. By late 2025, China's progress is real. DUV machines, clever workarounds, and AMES's global success are major victories. China is building a formidable domestic semiconductor industry, proving skeptics wrong, yet a vast gap remains. China's tools lag behind ASML, and its workarounds are too costly for mass production. Full-scale sub-10 nm chip making with a purely domestic tool chain is unlikely before 2030. The US and its allies still control the ultimate trump card, ASML's EUV machines. This gives the West continued leverage and strategic advantage. The technological decoupling is accelerating, with both sides preparing for a long conflict. China will keep pushing. More patents, incremental DUV improvements, and alternative EUV experiments. The question isn't if China will advance, but how quickly it can close a gap that took decades to create. The race is far from over. The outcome will shape the future of technology and global power.